Miss Coker, you're muted and I can't hear you.
Thank you. All right, so an angle in center position, we're going to have positive and negative angles today. Um, all the angles that we're going to graph today will be in the coordinate plane. Your vertex is always going to be at the origin, and your initial side is always going to be along the positive x-axis. Okay, there's two types of angles. You can have a positive angle, which has a counterclockwise rotation. It's opposite of what you think. Negative angles are going to rotate clockwise. So positive, counterclockwise, negative, clockwise. Okay, so if you look at the bottom, an example of a positive angle, your initial side, you always start on the positive x-axis. You're going to rotate around, and of course you can rotate around as many times as you want to. You're going to have angles 1070 degrees or an angle in radian measure. So of course you keep showing that rotation. If you have to go around multiple times, vertex at the origin, terminal sides where you end. Negative angle is going to start at the positive x-axis. It's going to rotate clockwise, and once again you can go around as many times as you need to get your angle measure. In the section, they're going to ask you to sketch or draw angles in standard position. So let's say they give you an angle of 300 degrees. You would just sketch your x and y axis, draw that, show that ray is your initial side, and then you just show the rotation around and draw your terminal side. Okay, you don't really have to write this part that's at the bottom. Does anybody need me to go back up? Okay. So this probably is common sense to you, but angles may lie in a quadrant, such as angle alpha that I have shown here. It's going to lie in quadrant 2. Angle theta would lie in quadrant 3, or an angle may end up being on an axis. And so in that case, it's called a quadrantal angle. Yes, that's what I was about to say. I don't know why my camera has been doing this so much lately. No, what? I know. It did that to me all day yesterday. I think it's my USB cable that's going bad or something. Okay, angles in our case are going to be measured in degrees, which you're very familiar with. But what you are not as familiar with is radian measure. And I'm going to show you where radian measure is derived from. All right, so we've got this circle. It has a radius r, and notice that this central angle intercepts an arc that also is the same length as your radius. So this is just an example of where a radian is derived from. So 1 radian measure is the measure of that central angle that intercepts the arc that has the same radius length. So later on in chapter 4, when you're going to hear pi over 3 and 2 pi and all of that, this in radian measure likes to be in terms of pi, because think about it. What's the distance around the circle? What'd you say? Good, it's the circumference. So if my circumference is 2 pi r, and let's say, of course, that radius has a length of 1, then the whole distance around the circle, or well, the degree measure around the circle would be 2 pi in radian measure if your radius is 1. And that's what it is on the unit circle. But when I was first studying radians, I was like, what in the world? It was just hard for me to wrap my mind around like what a radian is and where it comes from. Okay, this is the next thing I'm going to show you is a small formula on how you can get radian measure. And really all you need to do is write down like what I have underlined and what's in green, and you can draw that circle if you want to, but definitely write down this. So how you can get the radian measure of any angle, whether you leave it in terms of pi or whether it's in decimal form, the radian measure of any central angle theta is obtained by taking the length of the arc that central angle intercepts and dividing it by your radius length of your circle. So radian measure is the length of the intercepted arc divided by the radius. For this formula, you're going to use this in section 4.1 a lot. This formula, theta, is always in radians. So if they give you theta in degrees, you're going to have to convert to radians if you're going to use this formula or a version of it. S is arc length, R is your radius. So to get an angle measure, divide the arc length that it intercepts by the radius length of the circle. What do you think must be true about the length of S and the length of R? They must have the same what? S and R, your arc length and your radius length, you have to make sure they're in the same unit. So if one's in feet and inches, you're going to have to convert to one or the other. So always double check that. I think one problem in 4.1, you had centimeters and meters. All right, you don't even have to write that down unless you want to, or the bottom part here. I'm just showing you, for example, what an angle in degrees, which you're very familiar with that, versus what an angle in radians looks like. There shouldn't be any confusion of whether an angle is in degrees or radians. So this is how you'll see it in math. Of course, you'll have the degree symbol if it's in degrees. For radian measure, though, they're going to just say like theta equals 2.5. So if you don't see a degree measure there and they're talking about an angle, that is radian measure. Or they may actually write out 2.5 radians. So no degree symbol or the word radians, it's in that form. All right, you must still need this. Okay, I'm about to show you the relationship. Hopefully this will make more sense to you on where radian comes from. Okay, we've got a circle with radius r, and it intercepts. We're going to say that the whole arc, we want to find out what, and okay, well, let me back up. Tell me how many degrees is in a circle? How many degrees is in a rotation? 360. So we know, of course, that in degrees, this is 360 degrees. But if we want to find out what the radian measure is, you, of course, use your formula. We want to find out what this angle is. We know it's 360, but we want to find out radian measure. So we're going to say arc length divided by r. Well, what is the length of this arc that's intercepted? What's the distance around that circle? What's the circumference formula for a circle? 2 pi r. So we say that S is my arc length, and that is 2 pi r. So you take that, plug in. So 2 pi r divided by radius length. What happens to your r values? They cancel. So this angle in terms of radians is 2 pi. So the complete distance around the circle is 2 pi radians. So that means, of course, 180 degrees would equal how many radians? Pi. Good. So on the unit circle, that's why you see a complete rotation, of course, is going to give you 2 pi. Halfway around the unit circle is going to give you pi. And that's leading us into the next thing. That's what they use to convert. They use the basic. They don't use 2 pi equals 360, which 2 pi radians equals 360, but this is what they do. They divide both of them by 2 to get this conversion factor. 180 degrees equals pi radians. What'd you say?
When I came back, the attendance was
Good. I could have taken, if she would have done that, I think I could have taken you, I think I could have taken it out for you.
she's like, are you just something? I'm like, no, I can't.
To get, like, just the,
That and getting it.
Yeah, like I hope it's for one day. You go wear it on calm.
all right. The next thing we're gonna look at, this is what you use. All you need to do is write down this part. To convert from degrees over to radians, you're gonna use this conversion factor, pi radians divided by 180 degrees. If you remember unit conversion from science, I'm sure y'all did that in physics, chemistry, all of that. If you're going from degrees to radians, you want degrees to cancel, so it has to be on the bottom. Okay, most of the time when you're converting to radians, you're going to leave pi in your answer. and not actually type pi into your calculator. And you'll see what I'm talking about in a minute. But sometimes you will type in pi. So it's kind of confusing, but I'll show you what I'm talking about. Okay, if you're converting from radians back over to degrees, the easiest way is simply if you have pi, if you have 2 pi over 3 and they want you to convert that to degree measure, you can just plug in 180 degrees for pi. That's the easiest way I know to tell you. Plug in 180 degrees for pi and do the math. If you don't have pi in your problem and they give you like 3.4 radians, then you have to use this conversion factor and you will use pi in your calculator. All right, you must still need that. Okay, let's look at some examples before we move on. We're going to look at how to get a central angle in radian measure, how to convert from degrees to radians, and vice versa. You've got a central angle, theta, in a circle of radius 6 inches. It's intercepting an arc of length 2 feet. What is the radian measure of theta? So what is theta in radians? What was your small formula to find theta in radians? Good. It was S over R, and that's your arc length divided by the radius length. So they tell you that the arc length is 2 feet. The radius length is 6 inches. What's wrong with that? It's not in the same unit. So it doesn't matter if you want to convert 6 over to feet, get half, you can, or if you want to convert feet over to inches. Which one do y'all want to do?
24.
There you go, 2406. So theta in radian measure is 4. So you can either write theta equals 4, or you can write 4 radians if you want to. Okay, we're going to convert all of these from degrees over to radians. We have 150 degrees. Now, you're going to leave pi in your answer unless it's, well, they may, never mind. They ask you to leave it as a decimal, don't they? That's what I was thinking. So I'm gonna show you both ways. I'm gonna show you how to leave pi in your answer, and I'm gonna show you how to go ahead and convert it to a decimal. Go ahead and, anyway, 150, so we're going from degrees to radians. So you need to multiply, what's your conversion factor? Multiply 150 by what? Good. Pi radians over 180 degrees. what you're gonna do, if you're leaving pi, then you're gonna write 150 over 180 and leave pi alone. And you're gonna reduce 150 over 180. So you'll write your angle over 180, reduce it, leave pi every time. So what will this reduce to? There you go. So that's if you leave it in terms of pi, and this is the way you'll see it. 5/6 pi. If they want you to go ahead and actually leave it as a decimal, then you will type in 5 times pi in your calculator, divide it by 6, or 5 divided by 6 times pi, either way, and you get approximately 2.62 radians. Okay, part B, negative 225 degrees. If you're leaving it in pi, so you're going to say negative 225 over 180. Bless you. So leaving pi, negative 225 over 180, reduce that. These awesome calculators I have over here will do fractions very easily for you. So you get negative 5/4 pi. If you convert that to a decimal, you're going to say negative 225 times pi in your calculator, divide by 180. And that gives you negative 3.93 radians. Okay, how do y'all feel about converting from degrees to radians? What? Yeah, 4.1. I still gotta work the one. I gotta work that one that you asked about in GroupMe. From 4.2. 4.2, yeah, the one that they started you off with, and number 2 is kind of crazy. Okay, I want you guys to tell me what this one is just in terms of pi. You don't have to convert it to decimal. Just tell me what it is in radians in terms of pi. What? Mm-mm. Close. Yes. Okay, you have to multiply by pi radians over 180. And really all you're doing is taking a degree measure, putting it over 180 and reducing that. So look, do y'all know that pairs of zeros will cross off like that? So you're left with negative 4 over 18. So negative 2/9 pi. We're going to leave them in terms of pi, and like we're rarely ever going to convert over to decimal form like that. Okay, really quick, we'll move on to drawing angles. All right, let's convert from radians to degrees. My arrows all jacked up. Okay, -4 pi. I told you that if you have pi and you're converting to degrees, all you have to do is plug in pi is what in degrees? Good. All you have to do is plug in 180 if you have pi. So -4 times 180 is what? There you go. 720 degrees. So if you have pi, plug in 180. But sometimes they give you the decimal version of radians, such as the number 4. They're going to say 3.4 radians, and they want you to change that over to degrees. So in this case, you have to multiply by 180 degrees over pi radians, and you will use pi in your calculator. In this case, when you're going from radians to degrees, you will type in pi if it's like this. That's what's confusing about these problems. They're not hard, it's just you have to remember when not to use pi. All right, your radians cancel. So multiply 3.4 times 180 divided by pi, and it'll give you 194.81 degrees. Okay, do y'all have any questions about that? All right, the next thing that we're doing every year, some people always grasp it pretty quickly, and then it throws some people for a loop. Drawing angles in standard position. We've already talked about that a positive angle will go counterclockwise, negative angle goes clockwise. You need to show which way it rotates. So show a rotational arrow. And if you go multiple rotations, make sure you show that too. So show your rotational arrow. You can convert these to degrees every time if that helps you, because I know that's what you're more comfortable with than radians. All right, so every time you draw these angles, you're gonna sketch your X and Y axis. You're always gonna start on which side? Where are you gonna start every time? Good, you're always gonna start at the positive X axis. You're gonna rotate counterclockwise if it's positive, clockwise if it's negative. Okay, so in these problems, they ask you to draw each angle in standard position, which simply means your starting side is on the positive x-axis. You'll rotate to wherever your angle is at, or an approximate position. Draw your terminal side. Does anybody still need that top part here? Okay. What'd you say? This one? No, I was just saying you can convert it to degrees. If you don't want to work in terms of radian measure. Okay, so number 1, we have 3 pi, what? What'd you say? Oh, okay, I got you. All right, 3 pi over 4. Just draw a small XY axis. You're gonna start here. This is the first thing you're gonna do every time. Draw your starting side. Now, this is a positive angle, so we're gonna rotate counter clockwise. And to help you work in terms of radians, a full rotation in radians would be what? Good. This was, of course, you're starting at 0 radians. If you go all the way around, this is 2 pi radians. So if I rotate all the way here halfway, that's how many? It's just pi. So if I rotate, if I'm starting here at 0 pi radians and I rotate here to pi, then if I rotate 1/4 of the way, what is that? Good, that's pi over 2. And then if we rotate here, what will that be? What is, like, this would be pi over 2, another half pi, so 2 pi over 2 pi. Good, this will be 3 pi over 2. Just to give you an idea of how radian measure works. Okay, so roughly, where do you think 3/4 pi would be? If this is 1/2 and this is 1 pi, then 3/4 must be where? Good, it's gotta be right in the middle. So I've started this initial side, I'm gonna rotate and draw that terminal side there, so that I rotated this way. And then that will be 3 pi over 4. This is just introducing you to when we get into 4.2 and you're having to deal with like 11 pi over 3. You know, where you rotate, where that's at. That's what it's trying to help you visualize. All right, do y'all have any questions about that one? All right, number 2. Hang on, let me go back to number 1. If you did convert this to degrees, if you'd rather do that, you'd say 3 times 180 divided by 4, and that would give you 135 degrees. And this would be, what would be 1/4 of a rotation in degrees? What would that be in degrees? That would be 90 degrees. Half a rotation would be 180, 90 more to 70, and of course, full rotation 360. So 90, 135 is going to be halfway between them. All right, number 2. You've got negative 2 pi over 3. Always starting at the positive x-axis. Okay, this time we're going, this is a negative angle, so we actually have to go clockwise. We're going clockwise rotation. So if we do that, I'm starting at 0 pi. If I rotate here, what is this in terms of negative angle? You're close. Yeah, negative pi, good. Negative pi over 2. And then a rotation halfway around in the negative direction, this will be negative pi. So of course, all it does is just reverse them. And then negative 3 pi over 2. Okay, so to get a sense of where negative 2 pi over 3 is, 2/3 is really close to what? Or tell me what quadrant it should be in. Should it be in 1, 2, 3, or 4? Good. It's got to be in quadrant 3 because we're starting here and we're rotating this way. 2/3 is really close to 1 pi, but it's greater than 1/2. So 2/3, really close there. I'm going to say it's approximately here, because it's closer to 1 pi than it is to 1/2. Does that make sense? Okay, so we rotated this way. Now, once again, you can convert that to degrees if you wanted to. That would give you negative 120 degrees. And so 90, you'd rotate negative 90 and then 30 more. Probably a little bit. 90, 30, a little bit closer that way. The people that are like really OCD about being very accurate, like they don't like sketching stuff like this. Okay, do y'all have any questions about that? Hang on, I told you wrong. Like 2/3 is actually gonna be closer to 0.5 than it would be to 1. So that's why it should be closer this way. Does that make sense? Did anybody think that and not tell me? All right, last one we're gonna look at, drawing angles, positive 14 pi over 3. Okay, how many times do you think you're gonna go around? Good, you're gonna go around, this is approximately like 14 divided by 3 is 4.7. So this is approximately 4.7 pi. And you know that every half rotation, this is pi, that's pi over 2 or 0.5 pi. This is 3 halves pi or 1.5 pi, 2 pi, so on. Okay, so if we rotate all the way around here one time, then we're at 2 pi. Do you go around one more rotation? If you go around one more, like here, we're at 2 pi. And if we rotate all the way back around, we're going to be at 4 pi. And all we need to go back is we need to go to 0.7. That's all we have left over. We've rotated 2 pi, 4 pi. Where would 0.7 pi be? What quadrant? The second one. If you rotate to here, you're just at 0.5. So you got to go 0.2 more, just slightly into quadrant 2. So if you have one that you know is over one rotation, I would divide this and get the decimal. You know that every half rotation is pi or all the way around is 2 pi. So you just keep adding it up as you go. Well, yeah, it should be a little neater than that, but yeah. Start here, come back around. Yeah, it should look like a snail kind of. Okay, all right, and then you don't have to, I'm just showing you an example here. You don't have to write that down unless you just want to, but I would definitely write coterminal angles are two angles with the same initial side and terminal side. They have different rotations. Two angles, they have the same initial side and the same terminal side, but they have different rotations. So even in 4.4, 4.2, that you're going to have to deal with coterminal angles, and it will be easier in some problems for you to find an angle's coterminal match or coterminal partner. So I'm just showing you an example here. You've got this positive angle 60 degrees or pi over 3, and you've got this negative angle 300 degrees or negative 5 pi over 3. Those are coterminal angles. Of course, notice they've been rotated differently, but they both have the same starting side and they both end up at the same terminal side. So those are a good example of coterminal angles. 45-degree angle, tell me what negative angle would be coterminal with 45 degrees. What's left over? Negative 315 degrees would be coterminal with positive 45. So negative 315 degrees and 45 degrees are coterminal angles. All right, you don't have to write down this part in purple. I'm about to show you your formula in a sense, how to get coterminal angles. Okay, so increasing or decreasing the degree measure of an angle that's in center position by an integer multiple of 360 will result in a coterminal angle. That's what it says in your textbook. And all this means is if I take an angle such as 60 degrees and I want to find its coterminal angle, you can add 360 to this. So 420 would also be a coterminal angle with 60 degrees, or you can subtract 360 from that, and that's how you get negative 300. So when they say increase or decrease by a multiple of 360 to get a coterminal angle, that's all they're meaning. Okay, definitely write down this part. So two coterminal angles you can find infinitely many coterminal angles for any angle. All you have to do is keep subtracting 360 or 2 pi, or keep adding 360 or 2 pi. But for your directions in 4.1, they always want you to find an angle that is between 0 and 2 pi or between 0 and 360, meaning that they want a positive coterminal angle with the one they give you in the problem. So this is how you do it. If your angle is negative to begin with, then you find a coterminal angle by adding 360 or 2 pi. So if your angle is negative, you add 360 or 2 pi. If your angle is positive to begin with, then you're going to subtract 360 or 2 pi. Angle negative, you add. Angle positive, you subtract. Okay, find a positive Coterminal angle that's less than 360 degrees or 2 pi, that's coterminal with this one. So we have negative 765 degrees. We want our coterminal angle to be positive. We're starting out negative, so do we add or subtract 360? Good, you add 360, but you still wind up with a negative angle, so you have to do it how many times? You have to do it, good, you have to do it 2 or 3 times. So if we add 360 here, that's going to give you negative 405. You have to do it 3 times. So add 360. So when it said add integer multiples of 360, notice we're adding 360 3 times. So really you could just say like 360 times 3 and then add it. This will give you negative 45 degrees. We're still negative. They want us to be positive. So 315 degrees. And if you were to draw both of those angles, you would say they have the same terminal side, same initial. Number 2, we have negative. Don't pay attention to that. The easiest way, if you could notice that you need to add 360 3 times, would just be to multiply and then add it. But some people like to just do it like this, step by step. Add 360, add 360, add it. So 315 is your answer. Pi over 40, number 2. This is in radian measure. It's negative. So do you add or subtract 2 pi? Good. You add 2 pi. Find a common denominator. So what is this angle's coterminal angle? A 79 pi over 40. Are y'all okay with that, or am I losing you? What?
Yeah.
What'd y'all say?
Really weird.
Yeah, it is. Yeah, I agree. Is that why none of y'all are wanting to say it?
Yeah.
That's so true in math. When you get something off the wall, you're like, I don't want to say that. I'm pretty sure it's wrong. All right, 19 pi over 6. So this is a positive angle in radians. Find its coterminal angle. So do you add or subtract 2 pi? Good, it's positive, so we're going to subtract 2 pi. And also notice that 19 divided by 6, that's greater than 2 pi, and we're wanting an angle that's below 2 pi or 360. So find a common denominator of 6. So 2 pi turns into 12 pi over 6, and then you get 7 pi over 6. That one looks better than the last one. And always double check and make sure that 7, 6 is less than 2, and it is. So this is under 2 pi. Okay, do you have any questions? There's a lot of stuff in 401. There's a lot. It seems like every section in chapter 4 is loaded. Okay, the last thing we're going to talk about in 4.1 is linear and angular speed that deals with, of course, angles in radian measure, arc length, time, and all of that. I don't know if you may get to this if you're in physics or had physics, linear and angular speed, but an example that it gives in the book, it talks about a carousel, how it contains 4 circular rows of animals. And as the carousel revolves, the animals in the outer row travel a greater distance per unit of time than those in the inner rows. These animals have a greater linear speed than those in the inner rows. But all animals in the 4 circular rows will have the same angular speed. So there's some word problems in this section that deal with that. Pretty neat. Talk about things that rotate, and which I don't know if you'll think they're neat or not, probably not, but anyway. All right, how do you get linear speed? Linear speed is represented by this Greek letter that kind of looks like a V, and it's equal to S divided by T. What was S earlier? What did the letter S represent earlier? It represented the length of your arc. So how you get linear speed is you divide arc length by time. They're going to combine these two formulas in a minute. So notice that angular speed, which is the Greek letter, looks like a W, is theta divided by time. Theta is in what measure? You think theta is in degrees or radians? It is in radians. So if you're going to use theta in this formula, it has to be in radian measure. All right, let me scroll down. This is the main. So they're going to ask you to find linear speed in terms of angular speed, and this is your formula you're going to use. Linear speed is going to be equal to your radius length times whatever your angular speed is. Linear speed equals radius times angular speed. But you have to find your angular speed by saying theta divided by time. And this, of course, is just telling you what all of them stand for. Theta is angle in radians, T time, V is linear speed, W angular speed, all of that. Okay, in this example, they tell you that the radius of a wheel rolling on the ground is 80 centimeters. If the wheel rotates through an angle of 60 degrees, how many centimeters does it move? And express your answer in terms of pi and then round it to decimal places. So in this case, all they're wanting you to find is the length of the arc. So you've got this wheel rolling, its radius is 80 centimeters. How many centimeters does it move? So you're going to use that formula that contained arc length, contained an angle, contained your radius. But of course, you have to find, you're solving this for S. So say the S equals your angle in radians times your radius, which was 80. The first thing you have to do is convert that 60 degrees over to radians. So it'll be pi over 3. And then go through and plug in. So pi over 3 times 80, your radius length, and that's going to give you 80 pi over 3 centimeters if they leave it in terms of pi, or you multiply by pi and get 83.78 centimeters. So if it's just saying like you got this circular object, it's rotating, what distance did it travel? You're finding S, arc length. Okay, last example. You've got a Ferris wheel that has a radius of 25 feet. The wheel is rotating at 2 revolutions per minute. Wheel is rotating at 2 revolutions per minute. Find the linear speed in feet per minute of a seat on the Ferris wheel. So we know the radius length. They tell us how much it's rotating per minute, how often, and we're asked to find linear speed. So recall that linear speed is the radius length of your object times angular speed. But we have to find angular speed first. What was your formula to find angular speed? It was good. It was theta divided by time. Okay, so they tell you that it's rotating at 2 revolutions a minute. How many radians are in 1 revolution? Good, there's 2 pi radians in 1 revolution. So that's gonna make your revolutions cancel. Now we do have angular speed in terms of radians per unit of time, and that's always what it has to be in, is radians per unit of time. So they're talking about minutes, so we're good there. So you've got 4 pi radians per minute is how much your angular speed is. So we know that. Now go back and plug in, your radius was 25 feet times 4 pi radians per minute. So if they ask you to leave this in terms of pi, you would have 100 pi feet per minute. Otherwise, you're going to multiply by pi, 100 times pi, and well, that's divided by 1. So per minute, and that's going to give you approximately 314 feet per minute. So if the Ferris wheel broke off of its axle and rotated on the ground, it would travel 314 feet per minute. That would be bad if it did that. Yep. Okay.